Hi everyone. In this video, we are going to look at the size and Venn diagrams. We are going to have two parts for this topic. So this is the first part. Let's look at the definition of set. A set is a collection of a group of objects that meet certain requirements. Basically, a set is very much like a club in human society. In order to be a member of that club, you have to meet some requirements, right? It's not that everybody can join any club. There's a requirement, and those requirements or criteria have to be very clearly defined, so that for any given candidate, for any given object, we can determine very decisively if that object or candidate is a member of that club or of that set, right? So it's very much clear to the club. Now let's look at the example. The set of great US presidents. And if you look at this statement, actually it's not very clearly defined. The reason is this word great. The great is there's no very clearly defined criteria to say something is great or somebody is great or not. This is a very subjective word. So this statement cannot be used to define a set, because some people think a person a great president, some other people think it's not actually. So this is not clearly defined criteria. So this is not a set. Now look at another one. Another example, the set of live US presidents. And this is a valid set because everybody knows, this is a fact actually, which president is alive, which one is not. So all of the ones that are alive should be part of this set, should be the members in this set. And those people who are not alive anymore should not be in this set. So it's very clearly defined. And the last one, the set of male gateway students. So this is a set. So if you look at this requirement or statement, you can determine any given person whether that person should be a member of this set, because these criteria are very clearly defined. First, it has to be a male. Secondly, you have to be a gateway student. If you satisfy these two requirements, you are a member of that set. So this is the valid one. Another thing I'd like to mention before we move on to the next slides is that a set can only contain distinct members. That means you don't want to put repeating members in a given set. Okay, now move on to the next slides. After we learn the definition of set, how to represent a set. Basically, there are two different ways to represent a set. The first one is called roster method. Pretty much like a roster of a class. On that roster, list all of the students' names in that class, right? So in this case, if we use a roster method to represent a set, basically it just simply list all of the members inside a pair of braces. List them all. That's called a roster method. Now let's look at this first example. The set of odd numbers between 2 and 10. So if we just look at this requirement, first, you have to be odd numbers. Secondly, not only being odd numbers, those numbers have to be bigger than 2 and smaller than 10, between 2 and 10, right? So if you think about these two requirements, it's very easy to identify those qualified numbers. Bigger than 2, the smallest qualified odd number bigger than 2 is 3. Next one is 5. then 7, then 9. Then we stop here because the next one, 11, will be bigger than 10. So you can see I list all of these qualified members inside a pair of braces. And this is called a roster method to represent a set. This is answer apparently. Now another example, let's look at the second example here. The set of even numbers greater than 10. Set of even numbers greater than 10. So first, this is the roster method. We are supposed to list all of the members, right? So there's a small issue here. How can you list all of them if you have countless numbers? Say greater than 10, there are countless numbers, even numbers greater than 10. How do you list them all, right? Now the way we do it using this roster method is that first, you list the first few codified members so that when readers read your set, they can form a pattern. Then following that pattern, they can figure out the rest of members. First, we need even numbers and we need them to be bigger than 10. So the very first codified member is 12, right? 12 even number greater than 10. So I'm going to write the first few codified members, 12, 14, 16, 18, and so on. You need to list at least 3, maybe 4, maybe 5, so that people can form a pattern by looking at these numbers. So the rest, you just follow this pattern. So you use 3 dots to indicate that there's many, many more, countless more, as long as you follow this pattern. So this is the roster method to list the membership, the members that have countless occurrences here in the set. So this is a standard answer. Now let's look at the next example. Now this is also an example. The set of even numbers between 10 and 200. So after the first 2 examples, this should be relatively easy to do. And this time we have a finite number of members from 10 to 200. We're looking for even numbers. So the even numbers is no more than 100 numbers. So it's in theory, it is okay to list them one by one. But 100 numbers still allowed to write them one by one. If that's not tedious enough, how about we want those even numbers between 10 and 20,000? It's still finite, right? Then nobody wants to write them out one by one. So we still need another mechanism to write this kind of members using roster method. Just like in the previous one, we want to write the first few members that is codified. So we need even numbers, we need them bigger than 10. So we start with 12, then 14, then 16, then 18. Then again, we use this 3 dots to indicate there's many more following this pattern. But this time, since we have finite members in this set, we want to put a upper limit, which one is the last qualified member in it, which is 198, right? Smaller than 200, so 198. This way, we also list all of this, but not literally, right? But still, people can follow this pattern to figure out each one of those that should be in this set. Okay, this is about the first method to represent a set. There's a second method. The second method actually just description. Remember, when we define a set, all we need to do is provide very clearly stated criteria, requirements, so that we can determine whether a given object belongs to that set or not, right? So using this description method, all you need to do is make sure your description is very clear about the criteria. Okay, look at the first example. The set of voters who are 50 years old or older. So this one is very clearly defined. So there are two types of requirements here. First, you have to be a voter in the first place, regardless your age. If you are a voter, in addition to that, your age has to be 50 or above 50. So if you satisfy both requirements, you are in. You are a member of this set. So it's very clearly defined. So this is okay. This is valid set. Okay, now after we learn the basics about sets, now let's look at some new terminologies. We have a pair of them. The first one is called subset. So from our daily life, we all understand what a subset is. It's a portion of a bigger thing, right? Subset. Now let's look at the formal definition, because in mathematics, we have to define everything in a very accurate manner. So here is the definition for the subset. If every element is the same as membership, okay, member, they are interchangeable. If every element in set A is also in set B, then we say set A is a subset of set B. So here, AB is just the names of sites. Okay, just like humans, when you have more than one person to deal with, you better know that those people's names. Otherwise, it's very hard to communicate with other people if you have many different sites to work with, right? So usually we use a capital letter to name a set. So we have two sets, set A and set B. Now, basically what it says is that if everything A is also in B, then A is a subset of B. Everything in A is also in B, subset of B. Now, let's look at this example. A has three members in it, 1, 2, 3. Usually I use numbers to as an example to illustrate, to explain the concepts. Actually, a set can contain anything in it. I use numbers because it is the easiest thing for people to understand. Okay, set A has three members, 1, 2, 3. Set B has 1, 2, 3, 4, 5, 6, 7. Yeah, set B has 7 members. Now let's look at if it is true that everything in A is also in B. A has 1 unit, B has 1 unit, it's also in B. A has 2 unit, B has 2 unit. A has 3, B has 3. We don't care whether B has more or not, but everything in A is also in B. That's the definition of being a subset. So we can say decisively set A is a subset of set B. And that's it. It's very easy to identify as long as we know the definition. So set A is a subset of set B. It's ET. Okay, next example. We have set A equals set A has dog, rabbit, horse as members. Set B has dog, rabbit, horse as members. Now let's say if set A is a subset of set B. Basically, everybody can see that they contain exact same members, right? So in our daily life, when we say sub, usually it's a portion of a bigger part, right? It's not whole thing. But here you can see the two sides are the same side actually. They just have different names, right? But is set A a subset of set B in this case? Again, we make decision, we make judgment based on the definition. Definition says if everything in A is also in B, then A is subset of B. Dog in A, dog also in B. Dog in rabbit in A, rabbit also in B. Horse in A, horse also in B. Everything in A is also in B. So according to the definition, yes, set A is subset of set B. Yeah, answer is yes. And notice that even though in these two sets, they have same elements, the order are different. Inside, order makes no difference. It's all about membership. If they have same members in it, they are the same set. Okay, order doesn't matter. Look at the next page. Now we move on to the next terminology. It is called proper subset. First, definition. If every element in A is also in B. So far, this is the same definition in subset. Now, second part of the proper subset definition is that there is at least one element in B that is not in A. If this is the case, then A subset A, then set A is a proper subset of B. The key is the second part. First half is that everything in A is also in B. Second part says there's something else in B that is not in A. In other words, B has more than just have everything that A has. B has some extra. If this is the case, set A is a proper subset of set B. Look at an example here. Set A has dog, rabbit, horse. Set B, dog, rabbit, horse, chicken, frog. First, everything in A is also in B. And there are at least one in B that is not in A. In other words, B has some extras. So this makes set A a proper subset of set B. Okay. A is a proper subset of set B. Now, here's another question based on these two sides. Is set A a subset of B? Is set A subset of set B? What do you say? We make decision based on the definition, right? Everything in A is also in B. So the answer is yes. Set A is a subset of set B. Set A is also a proper subset of set B. Okay, move on. Now, next concept is called empty set. Empty set. Now, empty set means you don't have a member in that set. In other words, based on the requirements, based on the definition of that particular set, no object is qualified to be a member in that set. So in that case, we have empty set. We have empty set. And there are two symbols which are interchangeable to represent an empty set. Hold on, run out of ink. So for empty set, there are two different symbols. Either you use a pair of braces with nothing in it. So this is the empty set. Or you use this Greek letter, pretty much like this. These two are the same thing. Okay, now let's look at an example. Set A is the set of female US presidents. So two requirements. First, that person has to be a US president. Secondly, it has to be a female. Do we have anyone qualified? Apparently not, right? So this is an empty set. This is the example of an empty set. Another example, a set of whole numbers that are smaller than 10 and bigger than 15. Can you give me a whole number that is smaller than 10 at the same time bigger than 15? No, we don't have such number existed, right? We don't have them. So that's examples of empty set. Now this is I just made the symbol for empty set, either this or this. Either way is okay. Next one. Now here's a quick quiz. Is this empty set? We have 0 inside this braces. Is this empty set? The answer is no. The reason, empty set has no member in it. And we do have one, it is 0. So it's not empty. It has something in it. Okay, now next one. After we learned the definition of size and some related concepts and terminologies about size, now we are ready to look at the next topic, which is operations with size. If we cannot do anything about size, we don't learn it in the first place, right? We need to be able to do something with the size. So we are looking at operations with size. Basically, we are going to look at 3 of them. The first one is called complement. So the complement set of a given set. Then we look at the intersection of 2 given sets, intersection of given sets. Then the last one is the union of given sets. So 3 of them. The first one is a complement. But in order to understand this concept, complement, we have to establish another one first. That is called universal set. Universal set. A universal set is a set that contains all of the objects under consideration. For example, it's not a universal set is different than universe in real life. Okay, universe is everything, but universal only contain those objects that of our interest. For example, if I want to talk about different portions of gateway students, then gateway students, this is a universal set, because no matter I talk about female students, female gateway students, or male gateway students, or say gateway students under 20 years old, gateway students above 50 years old, they're all part of gateway students. So as a result, this gateway students is the whole thing, is the whole thing that I'm interested in. So that is our universal set. Okay, let's. There's a definition here. A universal set is a set that contains all elements that under consideration. Okay, example. Now here this U is the symbol for universal set. We also have another set A, maybe other set later on. But I like to emphasize that this U, we use uppercase letter to represent the universal set. This is a convention. In other words, you will use the same symbol U. You don't want to use any other letters. But for other individual sets, you're free to use any letter you want. But U is something like reserved for the universal set. Okay, our universal set now is dog, cat, rabbit, frog, bird. That means when we talk about set, we will not talk about anything that other than these 5 different animals. You cannot go outside this. Now our individual set is A this time, so call it A. It contains dog and the bird. Apparently, individual set is always a subset of universal set, right? Now let's see the definition. This is the explanation. What is called a complement of given set. Now the complement of set A, this given set, contains all other elements in the universal set that are not in A. The symbol for complement set is either you put a small c on top of the given set, or you put something that look like a comma on top of given set. These two again are interchangeable. They are being used by different authors of books, and they are in different textbooks, but they are interchangeable. They represent the same thing. Using plain English, what does this mean? Complement of set A. It means I want all of those members as long as they're not A. So everything outside A, that's the concept of complement of A. You want everything that is still in the universal set, but as long as they're not in A. So that's the concept. Now so let's look at the examples on next page. So let me redisplay this two sides so that you can see them to determine this answer. So the previous in the example put on the previous slides, universal set and say this universal set that's a given set A. The complement of A is that as long as we don't have dog and bird, the rest are the complement of A. So the way I do it is that I just cross out the members from A. Dog is from A, bird is from A. Everything else constitutes the complement of A. I just don't want A. I want everything else, in other words. So it's very easy to understand concept. Now the second operation is called intersection set. Intersection set. Now try to understand this. This is very good analogy in real life to help you understand this concept, intersection set. Between two sides. Can be among two sides actually, but in terms of concept, it's okay. So in the real life, say if you have two roads intersect, right? Intersect. This is a road, there's another road. This portion is called intersect, right? Intersection portion of the two roads. Now there's a common knowledge that this area of the road belongs to both roads, right? This is part of this road. This is also part of this road. And this is the concept of intersection set. In other words, in your intersection set, it contains members that is common to both sets. That is the concept of intersection set. Now, let's look at this particular example here. And the symbol for intersection, this operation is upside down U. For example, if you have two sides, A and B, you want to find the common elements that belong to both sides, you put this upside down U in between, A intersection B. This is one side. The membership are those elements that are common to both sides. Now let's look at this particular example. We have set A given 1, 2, 3, 4, 5, B 2, 3, 8, 9, 10, C, these three numbers. Then the intersection between A and B is 2 and 3. So let's look at intersection between A and B. So we're looking for common element, right? Now look at them one by one. A has 1. How about B? B doesn't have 1. So 1 is not common. 2, B has 2 also. 2 is common. And the 3 also is in B. So 3 common. 4 and 5, they are not in B. So that's it. A intersection B, just 2 members in it. So this intersection set. Now how about B and C? B intersection with C. So we are looking for common elements between B and C. Let's take a look. Actually, we can make a decision really quick. Everything in B is 10 or smaller than 10. But the smallest number in C is 12. There's nothing there. There's no way they can have any overlap. So there's nothing common here. So you don't see a 0 here. You just use this empty side symbol. Or you can write it this way, using that Greek letter. Either way is okay. So we have empty set for this intersection set. Yeah, that's the answer. Now the next one. This is just a graphical illustration of this the concept of intersection set and the concept of union set on the next page. First, this intersection. This is about intersection. Graphically, it goes like this. The universal set, usually we use a rectangle to represent universal set, the universal set. And we use a circle to represent individual sets that belong to universal set. So look at how I draw these two sides. We have set A and set B. Apparently, they are overlapped region, right? Overlapped region. And this overlapped region apparently belongs to A and B at the same time. So this common area. So this common area in graph is equivalent to common elements in two given sites. So this is just a visual representation of intersection. So if this is set A, this is set B, and this is going to be the overlap region, this is the intersection set. And if you look at here, using these two examples, I mean the two sides that we had from the previous page, 1, 2, 3, 4, 5, 2, 3, 8, 9, 10, that's in here. You can see set A is 1, 2, 3, 4, 5. If you look at what's inside this set A circle, 1, 2, 3, 4, 5, right? That belong to A. What's in B? We have 2, 3, 8, 9, 10, right? And what's in common? A intersection B, from here, we are looking for common elements, right? Apparently only 2 and 3 are common. Look at how we put this 2 and 3. This put 2 and 3 in this overlapped region, which graphically represent intersection between two sides. Make sense? 2 and 3 belong to set A, 2 and 3 belong to set B. That's intersection. Okay, next page. This one will illustrate the concept visually, illustrate the concept of union set. First, let's understand this union set first. A union set of set A and B is denoted as A union B. Say in the intersection set symbol, we use upside down U, but this one is just a regular capital U. Okay, this is not universal set, it's operator. Okay, A union B. A union B, this concept is that you basically combine A and B together to form a new set. That means you take every element from A and every element from B, put them all in this new set called union set. It's like a joint set. Okay. And say A union B contains elements from both side A and B. It's not a common element, just from both sides. You get every element from A and B, put them together back to this unit set, like joint. This is illustration. Example. If A is 1, 2, 3, B is 3, 4, 5, X, Y, and rabbit, then A union B, look at that. 1, 2, 3 are from set A. 4, 5, X, Y, rabbit, 4, 5, X, Y, rabbit are from B. Even though both sides have 3 in it, remember in the beginning, when we talk about the definition of a set, we say a set only contains distinct members. So if something repeating, we just don't want the actual ones. So that's why we just have 1, 3 in here. But all of these elements from two sides, every element from these two sides are in here. That's called union set. Now, in terms of graphical representation, basically is this. Originally, say if you imagine, originally you have set A. So all of elements belong to set A are in this circle. And originally, we also have set B, that is here. Every element that belongs to set B are inside this boundary of set B circle, right? But when we form a union set, we don't differentiate which element comes from A originally, which elements comes from B originally, because they all become member of a new set. And this is boundary of new set. See, these two dash lines, dash curve, they're gone because we don't differentiate which set they originally come from. They are all one set now. Which is this? Let me use a different color. This is the union of two sides. After we put them together, there's no boundary between these two individual sets anymore. This is your union set. That's blue one. Okay, now move on to the next one. So after learning the basic definitions, basic operations, now we are ready to do some exercise to better understand these operations. So let's say our union set is given from 0 through 10. And that's our union set. And then we are given set A and set B. So our first question, we have a couple of this. Our first question is to find the complement of A. So still remember the definition of complement set. Complement of A means we want everything except those in A. So that's going to be, I just look at what's A in it, then I compare this to the union side, to the universal side, as long as we don't have this 1, 2, 3, 8, the rest will constitute a complement because we want the rest. We want everything outside A. So we don't want 1, so it's 0 still there. We don't want 1, we don't want 2, we don't want 3, so 4 is okay. 5 okay, 6, 7, 8, we don't want 8, and 9, 10. So this is complement of A. So notice that complement of A and A together will make the original universal set. Actually, it is true that any given set and its complement set will put together to form universal set. Because if you have any given element, there's only two possibilities, and that element belong to A or not belong to A. That's why these two together will give you the original universal set. Okay, so that's the answer apparently. Next one, let's see what else operation we have. Now, we want to find the union, the intersection between A and B. And let's say, just for your convenience, I write this two sides on this slide is exactly the same as you see on the last slide. This time we are looking for intersection. That means common part. The common part, you still have this, right? Common elements. 1 is common apparently. So 1's supposed to be the answer, a part of the answer. Then 2 is not common. 3 is common. And 8 is not common. The final answer, just a set contains 1 and 3. So 1 and 3. And at point, I'd like to mention a piece of information here. And in some books, instead of writing A and B to indicate the intersection between A and B, in some other books, some other publications, they use the word and. And then most likely they are going to use a capital letter to make sure people don't confuse that with a regular and word. So A and B. These two are equivalent. When they say A and B, also means intersection. So just mention that so that you recognize it when you see one. Now let's look at our next calculation. This time we do A union B. Again, for the convenience, I read this A and B from the original problem. So we are doing A union B now. So let's say A union B. The concept is very easy. We just put, let me get a different piece of paper. So we're doing A union B. Union B is a joined set. You put everything from A and B into a bigger set. So I just copy this 1, 2, 3, 8. I get all of this. I need to get all of this too, but without repeating. So 1 and 3 repeating. So just put a 9 and 10 here. So this is the union set. Right? Very clear. And this answer. And let's look at the next page. We're very close to the end. Now this time we do a little bit something a little bit more complex. We want to do an intersection between A complement and B. So a little bit complex. So the goal, we can do this in two different ways. First, we do it in a step-by-step manner. We find out what's in the complement of A, then what's in the side B, then we look for the common element between two sides, right? So, and this is the original sides, I just recopy them here. Now I'm going to find the complement of A. Say, look at that. This is A. Complement of A means from 0 through 10 universal side, I don't want the 1, 2, 3, 8. I want the rest, and these are the rest. So there's a complement of A. Then I compare this complement of A, which is left-hand side of this operation, to side B. And I pick the common element in the section between this and this. So let's compare. I just put B in here, easy to compare. We want common ones. So A complement intersection with B. What's in common? 0, no 0 here. 4, no 4 here. 5, no 5. And 6, no 6. 9 is here, so 9 is common. 10 is here, 10 is common. So 9 and 10. And that's this solution. You can see that. And this is one way to do that. Actually, the best way to do things is from intuition. So if you feel it and you know it's right, it's fast way to do that. That will depend on your understanding of this whole thing. What does it mean? This intersection means common element between this side and this side. If you imagine that, if common to side, whatever the answers we have to be part of B in order to be common in B also, right? So that means I want those elements in B, but at the same time, since it's a complement of A, it cannot be in A. In other words, I only want those elements in B that are not in A. If you look at here, I want this elements in B that is not in A. This in B is also in A. I don't want this. This in B also in A. I don't want this. This in B not in A. I want that. This in B not in A. I want that. So that's much faster. If we understand the meaning of this, I want those in B but not in A. Okay. Now this is the last one for this part. Now we are solving for this one. Again, a little bit more complex, just like in the last question. I'm going to do twice. First one is step by step. Second one, we do it intuitively, just by looking at the meaning of this whole thing. Either way is okay. You don't have to follow one particular approach. So first, in this case, I want to find out A union B first. Then we do complement. Now that's the original information. This A, this is A, this is B. A union B, basically just one these two sides together. We did that before, so I'm going to copy it. 1, 2, 3. We have 8, we have 9, we have 10, right? We just join them together without repeating. Now, A union B complement. So we all understand the meaning of complement by now. Complement means I don't want this. I don't want any of this. I want those that are left in the universal set. Since our universal set just 0 through 10, so we still have 0. We don't have 1, 2, 3. We have 4. 5, 6, 7, and then that's it. To complement. See, that's finance. That's finance. There's a, let's do it in a more intuitively. Say these are the sites I have here. I want to do A union B complement. Since A union B is like joint A and B, it will include all of the members from A and B, and complement means I don't want that. You know, I don't want anything from A or B. So now, since the universal set is from 0 through 10, I just look at these members one by one to say if they're in A or B. If they're in any one of those, I don't want it. So 0 is not here, so 0 is okay. 1 is here, I don't want 1. 2 is here, I don't want 2. 3, I don't want 3. 4 is not here. 4 is not here. Now 4 is not in any of this, so I want 4. 5, same thing, I want 5. 6, same thing. 7, we don't have 7 here, so that's same thing. 8 is here, I don't want it. 9 is here, I don't want it. 10 is here, I don't want it. That's final answer. See that? It's very easy if we understand the meaning of it. Okay, this is the end of this video. See you guys in the next video.